Welcome to lecture number 4. In this lecture, we will discuss how to estimate the parameters of a linear regression model. In the earlier lecture, we had discussed that there are 3 parameters beta 0, beta 1 and sigma square. So, if you try to recall, in the earlier lecture, we had taken the model y is equal to beta 0 plus beta 1 x plus epsilon, and we had obtained n observations, say this here x1 y1, x2 y2 up to xn yn, and we assume that all these observations, they are going to satisfy beta 0 plus beta 1 xi plus epsilon I. This is the model that they are going to satisfy. And if you try to recall, we had created this diagram. This was x, this was here y, and then we had observed the point something like this and so on, and we wanted to fit here a line something like this, right, and we had given it a name, say x1, this is my x1 y1 and this is my here x2 y2. So, this line is now, in more technical term, this is the line which we want to fit, to be fitted, and this is essentially the line y is equal to beta 0 plus beta 1 x. So, in this case, we also had assumed that this epsilon I has got mean 0, variance sigma square, and we also assume that epsilons are IID. That means they are identically and independently distributed, right. At this moment, I am going to make an assumption that epsilon i's are IID and they are following a normal distribution, right. So, I can write down briefly that IID, epsilons are IID following normal 0 sigma square distribution, right. This means that all epsilon I, they have been observed from a probability density function normal with mean 0 and variance sigma square, and we also assume that they are independent. They all epsilon 1, epsilon 2, epsilon 3, epsilon n, they are mutually independent of each other, right. Okay, I would like to make here one note that when we are going for the least square estimation, this assumption of normal distribution will not be used there. When we are going for the test of hypothesis and confidence interval estimation, then only this assumption of normality will be used. And later on, when we are doing the maximum likelihood estimation, in that case, right from the first step, we will require the assumption of normality. So, that you have to keep in mind. Well, I will try to explain you as soon as I come to maximum likelihood estimation and ordinary least square estimation. So, under this setup, now we try to estimate the parameter. So, our now objective is estimation of parameter. Estimation of parameters. And you have to keep in mind that there are 3 parameters, beta 0, beta 1 and sigma square, that we want to estimate. Okay. So, now I am going to use here 2 methods or 2 approaches. One is method of least squares, and another is maximum likelihood estimation. Right. So, first we try to understand what is this method of least square. Now, in this graphic, if you try to see, we had said this is my random error involved with the first observation denoted as epsilon 1, and similarly this is my epsilon 2 and so on. So, if you try to see, in every observation I have got some random error. Now, principle of least square says that I would like to find out this line, this orange line, in such a way such that these random errors are minimum and most of the point they are lying exactly on the line. So, in the first case I try to use the method of least squares. Okay, so first let us try to understand what is the least squares estimation. The principle of least square says that we try to find out the values of parameter in such a way so that the total error is as minimum as possible and most of the points are lying on the line. So, if you try to see in this picture, the random errors in the first observation is epsilon 1, in the second observation this is epsilon 2 and so on. So, in case if you try to minimize the total error is summation I goes from 1 to n epsilon I. But can you really do it? If I say we have to minimize it, does it make any sense? We had assumed that some of the errors are in the positive direction, that is above the line, and some errors are in the negative direction, they are lying under the line. So, if you try to sum them up, their sum may be very close to 0, and that will be indicating that my observation do not have random errors. So, that is wrong. So, this idea does not work here. So, this is not meaningful. So, now how to do? So, let us try to consider and let us try to minimize I goes from 1 to n summation epsilon I square. Now, does this make any sense? Answer is yes. Why? Because we had faced the problem earlier because some of my random errors were negative. So, once I try to square them, the negative become positive and now I can easily minimize it. Well, at this stage who can ask that once I am trying to convert my negative random errors into positive random errors, then another option is that I can take the absolute value of epsilon. Yes, answer is yes. Yes, you can also minimize I goes from 1 to n absolute value of summation epsilon I. Yes, you can also minimize the sum of absolute errors, that is I goes from 1 to n summation epsilon I. And this is also available in the literature. This is called as least absolute deviation estimation technique, but in this course we are not going to talk about it. So, we will try to consider that we want to obtain the values of the parameter by minimizing sum of squares of the random error, right. So, the next question is how to minimize it. Well, I can use the principle of maxima and minima, right. So, let us try to use the principle of maxima minima and try to obtain the values of beta 0, beta 1 and sigma square. So, let me write this summation epsilon I square as a s of function of beta 0 and beta 1 I goes from 1 to n epsilon I square, right. This can also be written as a summation I goes from 1 to n y I minus beta 0 minus beta 1 x I whole square. Okay, the principle of maxima and minima says that we need to obtain the partial derivative of s with respect to beta 0 and beta 1, put them equal to 0, solve it and then check using the second order derivative whether the solution gives us the maxima or minima. So, exactly we are going to follow the same rule. So, if I try to obtain the partial derivatives first. Right. So, I try to obtain the partial derivative of this thing with respect to beta 0 and this will come out to be minus twice of I goes from 1 to n y I minus beta 0 minus beta 1 x I, and next I try to partially differentiate this s with respect to beta 1, and this turns out to be summation I goes from 1 to n y I minus beta 0 minus beta 1 x I times x I. Okay. And now I try to put it equal to 0, put them equal to 0, and I need to solve it. So, let me call this as say equation number here 1 and say equation number here 2. Right. Okay. So, if I try to solve this equation number 1, this can be obtained like as follows. Right. This is once I open the bracket, this gives me I goes from 1 to n summation y I minus n times beta 0 minus beta 1 times summation I goes from 1 to n x I, put it equal to 0. Right. And or I can write down this thing here as a summation I goes from 1 to n, say y I minus beta 0 minus beta 1 over n summation I goes from here 1 to n x I is equal to 0. Right. Or I can write down here say y bar minus beta 0 minus beta 1 x bar equal to 0. Okay. So, solving this thing, this gives me that beta 0 is equal to y bar minus beta 1 x bar. But this beta 0 can be known to us provided beta 1 is known to us, but up to now we do not know the beta 1. So, now I try to solve this equation number 2 and let us see what we obtain over here. So, now let us try to consider this equation number 2 and we try to solve it. The equation number 2 is summation I goes from 1 to n x I y I minus beta 0 minus beta 1 x I is equal to 0. And now, if you just try to open the bracket and if you try to solve it, we get here beta 1 is equal to summation x I y I minus n times x bar y bar upon summation x I square minus n times x bar square, and summation is I goes from 1 to n. Right. So, if you try to simplify it, this quantity is nothing, I goes from 1 to n x I minus x bar y I minus y bar, and this quantity in the denominator is summation x I minus x bar whole square. Now, keep in mind that this x bar and say y bar, they are simply our sample mean, means whatever the observations we had obtained based on that I can find out their sample means. So, x bar and y bar are known to us. So, now I can see one thing, that when we started our model y equal to beta 0 plus beta 1 x plus epsilon, in that model this beta 0 and beta 1 were unknown to us. But now I can see that once I have got the observations, using those observations I can find out the value of beta 1. So, this I take as an estimator of beta 1, estimator of beta 1. Right. In simple ones, estimator means that the value of the parameter that can be obtained on the basis of given set of data. So, I have here a parameter that is beta 1, but its value is completely unknown to us. Now, I am saying that using my observation, I can compute the value of beta 1 from this expression which I have written here. So, this is an estimator of beta 1. So, for the sake of simplicity, let me try to rewrite here, say beta 1 hat is equal to Sxy upon Sxx, where this Sxy is nothing but summation I goes from 1 to n xi minus x bar yi minus y bar, and Sxx is I goes from 1 to n xi minus x bar. So, now in the later lectures we are going to use this notation. So, what I have seen now, that we have obtained the value of beta 1 as beta 1 hat. Now, the value of beta 0 that we had obtained in the earlier slide, here like this one, this is going to be known to us only when beta 1 is known to us. So, now what I try to write down here, that this value of beta 0 can be known to us if I try to replace my beta 1 by beta 1 hat like this. So, now using this expression I can again estimate my intercept term. So, this beta 0 hat is an estimator of beta 0, right. Both this beta 0 hat and say beta 1 hat, they have been obtained from the principle of least square, or in this case we have minimized the distance, the vertical distance between the observed values and the line, something like here you can see, something like here you can see, we have minimized this thing, right. So, they are also known as direct regression estimators. This beta 0 hat is the direct regression estimator of beta 0, and beta 1 hat is the direct regression estimator of beta 1. They are also called as least squares estimates or least squares estimators of beta 0 and beta 1. Well, we have obtained this thing, but we do not know whether the values of beta 0 and beta 1 that we have obtained as beta 0 hat and beta 1 hat, are they really minimizing my random errors or they are maximizing it. So, for that we have to find out the second order condition. Here you can see I have got here two parameters and we are jointly estimating them. So, we need to check about the bordered Hessian matrix. So, the Hessian matrix of second order partial derivatives is defined here as a H, that can be a matrix of 2 by 2 with the partial derivatives of second order with respect to beta 0 and second order partial derivative of S with respect to d beta 0 and then beta 1, and on the second diagonal the partial derivative of S with respect to beta 1 square. And this term is going to be the same which is here in the, so this is going to be the same beta 0 beta 1 with respect to d beta 0 d beta 1, right. Well, and this matrix has to be obtained at beta 0 equal to beta 0 hat and beta 1 is equal to beta 1 hat. So, what I have to do? I simply have to differentiate it again and then substitute beta 0 equal to beta 0 hat and beta 0 and beta 1 equal to beta 1 hat in the normal equation that we had obtained here. And in fact, they are actually providing us a global minima, right. So, now you can see we have obtained the value of beta 0 and beta 1. So, now if I try to write down compactly, we had a model y is equal to beta 0 plus beta 1 x plus epsilon, and we have obtained a fitted model, and this fitted model is y is equal to beta 0 hat plus beta 1 hat x, and this model is called as a fitted regression model. Okay. Now, after this, I can obtain the fitted values. Fitted values. What is this fitted values? You see, when we conducted the experiment and we obtained the data, then there was some difference between the observed data and the line. So, if I try to make the earlier diagram here once again, say this was your here x, this was here y, and this was your here line, and the observations they were lying somewhere here, here, and so on, right. So, if you try to observe, this is suppose our x1, y1, and we expected that this value is going to lie somewhere here on this line y is equal to beta 0 plus beta 1 x. So, so we had observed the values x1, y1, but I am expecting that this value should lie somewhere here. Okay. So, the value of y which is obtained using the observed value of xi, this is the ith fitted value. Well, let me try to explain simple example. Suppose I have got here a data which I can write, say here, suppose, say here xi and say here yi. Suppose I have here 4 sets of data, right. I take here suppose y equal to xi equal to 1 and I obtain yi equal to 6. I take xi equal to 3 and I obtain yi equal to 10. I take xi equal to 6 and suppose I obtain y equal to 22, and once I take xi equal to 7, I obtain say yi equal to 21. And now, suppose after hitting the model, after obtaining the values of beta 0 hat and beta 1 hat, on the basis of these 4 pairs of observation, suppose I get here a model y is equal to 2 plus 3x. So, this means all these xi, yi, they are also going to satisfy this model. Okay. So, now I can obtain here the value of yi hat. How I can obtain? For example, my y1 hat, that is going to be, I will try to use this model. So, this is going to be 2 plus 3 times xi, this is actually here 1. So, this is going to be 5. Similarly, if I try to obtain here y2 hat, this is going to be 2 plus 3 times here 3. So, this is going to be 11. Similarly, y3 hat, this is going to be 2 plus 3 into 6 and this is 20. And similarly, y4 hat, this is 2 plus 3 into 7, this is going to be 23. So, after this I can write this point now here as say x1 and say y1 hat. So, these are nothing but my fitted values. And if you try to observe what are these values, I simply have fitted the model on the basis of given set of data. Then using the given values of xi, I am trying to obtain the values of yi, which are yi hat. So, yi hats are the values of y which are obtained from the model, and they are called as fitted values. So, I can write down the fitted value here as say y hat is equal to beta 0 hat plus beta 1 hat, and now I am using a given value at x equal to xi. So, this is my ith fitted value. So, this is essentially my ith fitted value. Okay, now let us try to see a different aspect. now I can find out the difference between yi and yi hat. So, yi is the observed value and yi hat is the value of y which is obtained from the model. So, in this case if you try to see, I try to say denote it by here ei, and suppose I define it yi minus yi hat. So, this becomes here 6 minus 5 which is equal to here 1, this becomes here 10 minus 11 which is equal to here minus 1, and similarly this becomes here 22 minus 20, this is 2, and this becomes 21 minus 23 is equal to minus 2. These values are called residuals, and I try to denote it by here say ei. So, ei is nothing but the difference between yi and yi hat, and in general I can define E as a residual, the difference between observed and fitted values. So, this is my residual. Now, this residual has a very important property. If you observe in this picture, I am saying the difference between y1 and y1 hat now as per this definition is nothing but E1, and earlier we had denoted the same distance as say epsilon 1. So, you can see here that these residuals are going to act like as we have observed the random error in my data. Remember one thing, residuals are random variables, errors are random variables, and I am not estimating the random errors by residuals, but they will look like as if they are the values of random errors, and these residuals helps us a lot in obtaining the information about my random errors. And this we will try to discuss in the forthcoming lectures. Till then, goodbye.